Hello students. So in this session we'll talk about the solutions that were given as an assignment. So this is your tutorial session for the fourth unit. So, so I've already shared with you the questions. So let us look into the solutions. So the first question is, for a certain transmission line the propagation the phase constant beta is given and the characteristic impedance is 50 ohm. So as alpha value is not given here, we can assume it is a lossless scenario. Okay, so it is a lossless case, and the transmission line few parameters are given here. So that is, the total voltage at a location z is equal to -1 is given, and the reflection coefficient at z is equal to 1 is given, and the question asks for what is the total current at z equal to 0. So first of all, on any line we had the expressions for total voltage and total current. So the voltage on a line V of z can be written as V naught plus times e power minus j beta z plus V naught minus times e power plus j beta z, right? So this is your forward wave and this is your backward wave. So what is I of z? So we had also expression for I of z. So that is nothing but V naught plus times e power minus j beta z divided by z naught minus V naught minus of e power plus j beta z divided by z naught. So this is your current equation at any location. So here beta is given. So beta is given as pi by 2 and z naught is also given, which is 50 ohms. So all you have to do is substitute these conditions here and you get the answer for it. So what is V at z equal to -1? So if I put z equal to -1 in this question, I can see that I get V naught plus e power plus j beta, because if I put z equal to -1 I get plus j beta plus V naught minus times of e power minus j beta. But if you can see, beta is nothing but given as pi by 2. So in place of beta, if I replace it with pi by 2, okay, if I replace it with pi by 2, this simply becomes e power j pi by 2 is j and e power minus j pi by 2 is minus j, right? So from that you get v naught plus times of j minus v naught minus times of j. So this is nothing plus v naught plus minus v naught minus times of j, but this is given as 6 times of j. So that gives me a first equation, that v naught minus or v naught plus v naught minus is equal to 6. Of course I can solve for the other equation. So other condition is given as the reflection coefficient at z is equal to -1 is minus 0.25. So what is the reflection coefficient formula at any value of z is nothing but the reflected wave divided by the incident wave. So I can see that we want the reflection coefficient at z equal to 1. So if I want at z equal to 1, so it is simply this thing we are left with, z equal to 1, because beta is pi by 2. In place of beta, let me put pi by 2 here and pi by 2 here. I can see that I get v naught minus by v naught plus, and this is minus j, and in the denominator I get a j. So that is nothing but v naught minus by v naught plus with a negative sign, and this is given as minus 1 by 4, which is 0.25. So the other equation I get is v naught minus by v naught plus is 1 by 4. Right, so I have these equations, but what I want is I want the current at z equal to 0 location. So at z equal to 0, so I at z equal to 0 is the total current. So if I put z equal to 0 in this, I simply end up with v naught plus minus v naught minus divided by z naught. Okay, I can see that because it's by z naught which I want. So in fact I don't have to find the V0 and V0 minus values here, because already I have the expression for V0 plus and V0 minus. Okay, so I have this expression that V0 plus minus V0 minus is nothing but equal to 6. So that is 6 divided by the impedance is taken as 50. So what is the total current is 0.12 amperes. So that is your answer. So this is how you solve the first question. Of course, if at all we had some other values here, we might have to solve the values of V0 plus and V0 minus, and when you can substitute there and you get the answer. Okay, so this is about the first question. So we'll move on to the next one. So in this question, the transmission line of some unknown length and is terminated at Z is equal to 1 with a load ZL, and the characteristic impedance is given and the beta is also given. So the current I of Z and V of Z exists on the line, but all we know is the value of Z equal to 0, reflection coefficient at Z equal to 0 is 0.25. They're asking you to find the value of load ZL. So there are two ways in which you can do it. Okay, because it's a lossy line, I can say the magnitude of the reflection coefficient and the reflection coefficient at the load are same, and depending upon the phase change I can calculate what is the impedance change. But anyways, we'll move on with the first method, the straightaway method. So that is here you can see that at Z equal to 1, at Z is equal to 1, so reflection coefficient at any point on the line is basically given as we have seen previously, is nothing but for a forward, for a reflected wave, V0 minus into e power minus j beta, sorry, plus j beta z divided by V0 plus into e power minus j beta z. So this is your reflection coefficient at any point on the line. So all I can see is what is the reflection coefficient at Z equal to 0. Okay, at Z equal to 0, the reflection coefficient is given by V0 minus by V0 plus. Right? So because if you put Z equal to 0, e power 0 goes to 1. So this answer is given as j times of 0.25. Right? So that is what we have. But where is the load? Load is at Z equal to 1. So at Z equal to 1, the value is V0 minus by V0 plus times e power plus j beta divided by e power minus j beta. So beta is given as pi by 4. Okay, so this e power minus j, if I take it to the numerator, I get simply e power plus 2j beta. So if I put beta equal to pi by 4, so this becomes 2 and 2, I get e power j pi by 2. So e power j pi by 2 is nothing but equal to j. So this is the reflection coefficient at load at Z equal to 1. So at load we can also write the reflection coefficient as ZL minus Z0 divided by ZL plus Z0. And from the V0 minus V0 expression, so this value is nothing but j times of 0.25. So I can say this whole number is actually equal to minus 1 by 4. Okay, so I have ZL minus Z0 divided by ZL plus Z0 is equal to minus 1 by 4, and the value of Z0 is also given, it is 50 ohms. So let me write the answer. So what you'll get 4 times of ZL minus 200 is equal to minus ZL minus 50. So you have 5 ZL is equal to 200 minus 50, so that is 150, right? So 150 divided by 5, so you get ZL is equal to 30 ohms. So that is your answer. Right, we'll move on to the next problem. So in this question we can see that again a transmission line with some characteristic impedance is given, and it is a 50 ohm line, and the propagation constant is given and some length is also given. So the voltage at Z equal to 0 is given, the total voltage on the line at Z equal to 0 is given, So they're asking you to write what is the v plus of z and v minus of z, and what is the reflection coefficient of z, and so on. So first of all, what is the total voltage v of z can be written as voltage for the forward wave plus the voltage of the backward wave. Okay, so which is what we have written as v naught plus into e power minus j beta z plus v naught minus into e power plus j beta z. So they are asking you what are these equations. Okay, and what is the reflection coefficient? So the reflection coefficient is nothing but that reflected wave at any point divided by the the backward wave divided by the forward wave, right? So that is what you have to do. So here we need to calculate these functions in tau of z. So first we'll try to find what is v naught plus, because beta is given. So beta is given as pi by 2. All you have to find is what is v naught plus and v naught minus to get the answers here. So I have two conditions here. So it is given that at z equal to 0 the total voltage is given. So let us try to see what we can get from there. And also the other thing is I have the reflection coefficient at z is equal to 0. At z equal to 0, what will be the reflection coefficient? So if I put z equal to 0 here, so this is v naught, v minus is nothing but v naught minus into e power plus j beta z divided by v naught plus into e power minus j beta z. And if I put z equal to 0, this goes to 1 and the denominator also goes to 1. So I have v naught minus by v naught plus. But what is reflection coefficient at load? That is nothing but zl minus z naught divided by zl plus z naught. So I can see that zl is 150 minus 50 divided by 150 plus 50. So I get 100 by 200, so which is nothing but 1 by 2. So I get that v naught minus by v naught plus is exactly equal to 1 by 2. So that is one equation I have. So let me take the other equation, that at z equal to 0 the total voltage is given. So at z equal to 0, let me write the total voltage, that is v naught plus. If I put 0 here, okay, so e power minus e power 0 is 1. So I get v naught plus v naught minus is basically equal to 3 times of j. So with this I have v naught minus is v naught plus by 2. So if I put it there, so I get from this equation what I'll get in v naught minus I get 3 v naught plus by 2 should be equal to 3j. That makes v naught plus is equal to 2j and v naught minus is equal to j. So I have the values for v naught plus and v naught minus, so you can see the complex constants I have. So from this, can I write the total voltage for, so the question asks for what is v plus of z. So v plus of z is 2j e power minus j, beta is pi by 2, so it is minus pi by 2 times of z is one answer, and v naught minus is j times of e power plus j pi by 2 of z. And what is tau of z? You need just to divide these two. If you divide these two, right, if you divide these two things, you get j cancels out, you will be left with 2 times of e power, okay, I mean sorry, if you divide, you get 1 by 2 times of, my bad, 1 by 2 times of, so backward wave divided by the forward wave. Maybe I'll write them. So the backward wave is j e power plus j pi by 2 z divided by the forward wave is 2j e power minus j pi by 2z. So I can see that j gets cancels out, I get 1 by 2, and if I take this e power minus j pi by 2 to the numerator, so I get e power plus j pi z. So that is my reflection coefficient at any point of z. So I have the values for from the first one. So the next question asks for what is the complex functions v of z and I of z. So I have the expression for v of z here. So what is v of z? So v of z is v plus of z plus v minus of z. We already have the expressions for those things. So let us write those expressions so that I get v of z is nothing but 2j times of e power minus j pi by 2 times of z plus j times of e power plus j pi by 2 times of z. If this is the voltage, what about the current? So the current expression is you need to divide the forward wave with z naught. So it is 2j e power minus j pi by 2 of z divided by z naught is 50, and for the backward wave you divide it by minus 50, so you get j e power plus j pi by 2 times of z. So these are the equations for voltage and currents. So if you want impedance at any point, how do you get the impedance at any point? So the impedance at any point is simply voltage divided by current. Okay, so z of z is nothing but the division of these two. So if you divide these two, I basically get, so it is v of z divided by of z is impedance at any location. So if I divide, I get 50 into 2j e power minus j pi by 2 z plus j times of e power plus j pi by 2 z divided by 2j times of e power minus j pi by 2 z minus j times of e power plus j pi by 2 z. So this is your impedance at any point. So next the question asks for what is the value of v plus and v minus at tau equal to minus 1. So we have all the expressions here. So for v plus at z equal to minus 1 is nothing but, I put z equal to minus 1 there, I get 2j into e power plus j pi by 2, so that is 2j into j, I get minus 2. What is v minus of z? V minus of z at z equal to minus 1, of course. At z equal to minus 1, that is again you put j times of e power minus j pi by 2, you'll get, so you get minus j, so j into minus j, you get 1. So you have the voltages. So if you ask me what is the reflection coefficient at z equal to minus 1, so I can put z equal to minus 1 in this equation. You can see it becomes 1 by 2 into e power minus j pi, so basically which is again a minus 1, so you get minus 1 by 2. So I have the values for this one also. So the next thing is what is the total voltage at z is equal to minus 1. So I don't have to find the total voltage again, okay, because I know the total voltage at z is equal to minus 1 is nothing but the forward voltage at z is equal to minus 1 plus the backward voltage at z is equal to minus 1, which we have already calculated. So it is minus 2 plus 1, so it is 1 volt. In the same way, if you ask me the current, so here in this equation, so to write the current, so current at z is equal to minus 1 is nothing but the value of the voltage, forward voltage, divided by 50 minus, right, minus 1 by 50 minus the backward voltage, okay, because you get a minus, because for the backward voltage in the current expression you get a minus, and you can see, of course you can always put z is equal to minus 1 in this expression and you can get back the same equations. So you can see I have an answer for this. So the current is minus 3 by 50 amperes. So I have the value of voltage and currents, so all I have to do is to find the impedance, okay. So what is the value of impedance? So impedance is so the impedance at z is equal to minus 1, we need to calculate. One second. Yeah, so as I was saying, so the total voltage here, I have the total voltage at Z equal to -1. Here I made a small mistake here. You can see that is -2 plus 1. It's actually -1. My bad, I wrote a 1. So it is -2 plus 1 is -1 volt. So I have current at Z equal to -1. I have -3 by 50. So the line impedance Z is equal to Z is equal to -1 is nothing but voltage at Z is equal to -1 divided by current at Z is equal to -1. So that is -1 divided by -3 by 50. So answer is 50 by 3. In fact, to check whether we had the right answer or not, you can see that because here beta is pi by 2, okay, what happens for the length beta into L? So because it's a length of 1 meter, beta into L is becoming pi by 2. When can this happen? This can happen when beta is 2 pi by lambda, and L is also, if you take a lambda by 4 line, then you can see you can exactly end up a beta L is equal to pi by 2. So that means this 1 meter is actually a lambda by 4 in this scenario. So for a lambda by 4, if you remember, the input impedance expression is Z0 square divided by ZL. So Z0 square is 50 into 50 divided by ZL is 150. So you'll end up with an answer of 50 by 3. So that is what we had here also. Okay, so that means our analysis is right. Okay, so let's move on to the next question. So these questions are regarding the boundary conditions. So here some transmission lines are given, and in these transmission lines in the middle are connected with some kind of circuit element whose dimensions are very much small than the wavelength, so you don't have to apply transmission line analysis for these links also. Okay, obviously the connecting wires are treated as transmission lines, so I'm saying that these wires, there is no necessity of these wires which I have highlighted here to consider them as a transmission lines. They are simple connecting wires where you can still use your network theory. So, or you can neglect the transit time effect in this section. In this section, you can neglect the transit time effect. So that is what I mean when I say that this circuitry with the resistor here as a circuit whose dimension is very much small than the wavelength. That means you don't have to worry this as a separate transmission line analysis and transit time effects. You can consider it by taking it as a simple resisting network, right? Network analysis of phase here. But of course, there are transmission lines connected to this network. So the thing is, the voltage on this line is given. So on the line, the voltage equations are given for Z less than 0 and for Z greater than 0. The equations are given. So the question is, determine this constants V0, VA plus and VB minus. So what I can do is exactly at Z equal to 0, I can see that at Z equal to 0. Okay, so maybe at Z equal to 0, this location, according to this equation, for Z less than 0 and for Z greater than 0, at Z equal to 0, the boundary condition should hold. So if I assume that at this notion, what is a voltage, I can have what is the total voltage. So because for Z less than 0, this is the equation. So at Z, so less than 0, for Z less than 0 condition, I can see that at Z equal to 0, the voltage is VA plus 2. Okay, for Z greater than 0, the voltage at 0 condition is like -1 plus VB minus. So here the voltage is VA plus 2, and here the voltage is uh, -1 plus VB minus. Okay, so here you can see that the values, I have the voltage values. Okay, but of course, until unless I don't have the values for current, I cannot solve the equation so that I can get these unknown values VA and VB. So from this, what I can say is the potential difference between these 2 points is basically, or I have here I have some potential and here also I have some potential, and there is a 3 Z0 resistor here. That doesn't give me any answer. Okay, what I can get is, if I can know what is the amount of current that is flowing in, then maybe I can get the answer for these things, right? So let us find the current here. So because I have the voltage expression, so for z less than 0, what will be the expression for current? So here, what is a forward wave and what is a backward wave, that decides the issue here. So here VA plus is the forward wave. So as the notation is already predefined here, I can say that the current is VA plus e power minus j beta z divided by z naught. Okay, and minus divided by z naught times of the backward wave, that is 2 e power plus j beta z. So this is for z less than 0. So for z greater than 0, what will be the current equation? So it's again minus 1 e power minus j beta z. Okay, so because this is your uh, backward wave, okay, or sorry, if this is your forward wave, okay, so the forward wave is given, you divided by z naught, and for the backward wave you divide it by minus z naught, so you get Vb minus times of e power plus j beta z. So if you ask me what is the current equation at z equal to 0 in this scenario, right, at z equal to 0, the current is like Va plus minus 2 divided by z naught. Okay, so this is your current at z equal to 0. So I can say that into this port I can assume that a current is going off like Va plus minus 2 divided by z naught. Okay, so here still you are saying that this is a forward wave, okay, because you're still looking in the z direction. At this location, what is the current I will have? So ఈ location దగ్గర current ఎంత ఉంటుంది అంటే, so that is for z less than 0. For z greater than 0, if I put at z is equal to 0 scenario, I get a current of minus 1 by z naught minus Vb minus by z naught. Okay, so it is minus times of 1 plus Vb minus divided by z naught is the current. Okay, so with these values, so let me draw the network which you can see here. So the network I can see is like this. So in the network, I have a 3Z0 network, and I can say here, maybe let me put up thing here. So this is Va plus 2, and here this is some minus 1 plus Vb minus, and I'm saying the current here in this direction is Va plus minus 2 by Z naught, and I'm saying here the current here is minus 1 plus Vb minus by Z naught. So all I can see is there is a network here, and I have to solve this network to get my answer for the values of Vb and Vb minus. So because it's a resistor, so the current, whatever current is entering, should be equal to the leaving. So I can say that Va plus minus 2 by Z naught should be equal to minus of 1 plus Vb minus by Z naught. So if Z naught cancels out, I have the statement like Va minus, or sorry, Va plus, so Vb minus is equal to minus 1 plus 2, so that is equal to 1. So this is one equation which I get. Okay, so let me get the other equation. So the other equation is simple, because I see that there is some potential difference. Okay, if I assume this is my current, okay, so the potential difference is Va plus 2 minus, if I assume minus 1 plus Vb minus as your potential difference, divided by 3 times of Z naught, should be equal to the current that is flowing in, that is Va plus minus 2 divided by Z naught. So if I see Z naught cancels out, so this simply becomes, so maybe I'll write it here. So let me write this equation here. Va plus Vb minus is equal to 1. And this from this equation what we get here in the numerator, I can see that there is Va plus minus Vb minus, and there is plus 3 should be equal to, I'm getting Va plus minus 2. So if Va plus goes out from this equation, I get that Vb minus is minus 2 minus 3, that's minus 5. So Vb minus is 5, and that gives me Va plus as minus 4. So I have the answers for Vb minus and Va minus. So this is how you do by substituting the boundary conditions here. So the boundary is like, at this boundary what is the voltage, and at this boundary what is the voltage, at this boundary what is the current, and at this boundary what is the current. So those are the things you account for in our voltage equation, and you solve for the unknown values.